Imagine a helium balloon tied inside a car. When you hit the gas and accelerate forward, you might expect the balloon to be pushed backward, just like you are pressed into your seat, but it actually lurches forward. Because the air inside the cabin is much denser than the helium, that air has greater inertia. As the car accelerates, the heavier air resists the forward motion, pooling at the back of the car. This creates a high pressure zone that physically pushes the lighter helium balloon toward the front. Gas feels immaterial, but it is matter. It has mass, it has density, and it obeys Newtonian mechanics. Quantifying the state of this invisible matter requires a specific physical coordinate system. To describe the physical presence of a gas, we measure its pressure and volume. To describe its internal energy and quantity, we measure its temperature and moles. When calculating these variables, it is crucial to distinguish the baseline conditions. Standard temperature and pressure, or STP, is used for gas law calculations and is set at 273 Kelvin, or 0 degrees Celsius. This is distinct from standard state conditions used in thermodynamics, which occur at a warmer 298 Kelvin. Mastery of these systems moves past the rote manipulation of equations. It requires identifying the microscopic kinetics driving these formulas and knowing exactly when the ideal models physically collapse. Succeeding on the MCAT requires the ability to predict how invisible, chaotic molecular mechanics scale into measurable macroscopic phenomena. We begin with the ideal gas law. PV equals nRT is the engine from which proportional gas relationships are derived. By holding temperature and moles constant, squeezing a gas into a smaller volume increases pressure, tracing the hyperbolic curve known as Boyle's law. If we lock pressure and moles instead, we isolate Charles's law. Heating a gas increases its volume, tracing a linear upward slope. Resetting again, locking volume and moles derives Gay-Lussac's law, where heating a gas in a rigid container identically increases pressure. In a clinical setting, these theoretical pressures are continuously measured mechanically. When you read a patient's blood pressure using a sphygmomanometer, you are quantifying this exact physical force using millimeters of mercury. These individual laws are essentially boundary conditions, specific mathematical outputs generated by holding different state variables constant within the ideal gas law. But how do billions of randomly moving, colliding particles create perfectly stable macroscopic variables like a uniform pressure of 1 atmosphere? To answer this, we define macroscopic temperature strictly as the average kinetic energy of the molecules. We must discard the colloquial idea of heat and look purely at kinetic motion. This chart shows the Maxwell-Boltzmann distribution of gas particle speeds at a specific temperature. While average kinetic energy is stable, individual molecules travel at varying speeds. Increasing temperature raises average kinetic energy, flattening the curve and shifting it right as molecules travel faster. Now consider two different gases, one heavy, one light, held at the exact same temperature. Their average kinetic energies are identical, but their speed distributions look entirely different. Kinetic energy equals 1/2 mass times velocity squared. If average kinetic energy remains constant, but the gas particle's mass is large, velocity must drop. Heavier molecules travel slower than lighter ones at the same temperature. Graham's law governs diffusion, gases mixing through an open medium, and effusion, gas escaping through a tiny pore under pressure. Larger mass always means slower movement. Predictable macroscopic properties exist purely because we are observing the statistical averages of billions of chaotic microscopic collisions. In reality, gases rarely exist in pure isolation. When we transition to real-world mixtures, we apply Dalton's law of partial pressures. Dalton's law states that ideal gases in a shared container essentially ignore one another. The total pressure of the mixture is just the sum of the individual partial pressures each gas exerts independently. This partial pressure directly dictates how a gas interacts with a liquid. According to Henry's law, a gas's solubility in a fluid is directly proportional to the partial pressure of that gas hovering above the liquid surface. Hyperbaric oxygen therapy is a direct application of Henry's law. By placing a patient in a sealed chamber, we apply extreme external pressure. This drastically increases the partial pressure of oxygen, forcing the gas to dissolve directly into the blood plasma in high concentrations. The exact same physical constraint governs normal breathing. At the alveoli in the lungs, gas exchange relies on these partial pressure gradients. Oxygen moves passively down its gradient into the deoxygenated blood, while carbon dioxide moves out into the lungs to be exhaled. The human body doesn't spend cellular energy to transport these initial gases. It actively relies on the passive physical constraints of Dalton's and Henry's laws to sustain biological life. But the entire ideal gas model is built on two mathematically convenient assumptions: that gas particles take up zero physical volume, and that they exert zero attractive force on one another. At standard room temperature and pressure, these assumptions are statistically valid because the particles are far apart and moving fast. But at extreme limits, the ideal model collapses. Look at this pressure-volume graph. The smooth hyperbolic curve represents ideal theoretical behavior, but the actual measured behavior of a real gas kinks and deviates sharply as the volume decreases. The first failure point happens at high pressure. When thousands of particles are compressed into a microscopic box, they are packed tightly against one another. At this level of extreme compression, the physical size of the molecules themselves is no longer negligible. The gas particles take up absolute space, forcing the real gas to occupy slightly more volume than the ideal math predicts. It cannot be compressed to zero volume. The second failure point happens at extremely low temperatures. As temperature drops, the particles lose kinetic energy and slow down. Instead of bouncing cleanly off one another, they begin to be trapped by intermolecular attractive forces. They stick together slightly, hitting the container walls with less impact, resulting in a lower measured pressure than the ideal equation expects. The ideal gas law calculates an impossible, frictionless universe. Describing the measured reality of extreme compression and freezing requires an entirely new mathematical patch. The van der Waals equation serves as a structural patch to PV equals nRT, integrating the physical constraints of real-world molecules that the ideal model ignores. This equation addresses the two fatal assumptions. The A term corrects for attractive forces between polarizable molecules. Stronger dipole interactions mean a larger A constant. These forces act like a magnetic tether, slowing particles before they hit the wall, accounting for the lower pressure. Next, we look at the volume bracket and isolate the B term. This corrects for the physical size of the molecules. You can remember B for big particles. By subtracting NB, we mathematically remove the actual physical volume occupied by the particles themselves. What remains is only the true empty space available for the gas to compress into. The brilliance of this structural patch is its backward compatibility. Setting A and B back to zero collapses the entire equation perfectly back into the ideal gas law. Memorizing PV equals nRT is expected, but understanding precisely how intermolecular forces and physical particle size break that equation at the physical limits is the true mark of mastery.